So now that we talked about the precipitation reactions and we also talked about acid-base neutralization reaction, in Unit 7, we're going to talk about oxidation reduction reaction, which is kind of chemistry that focuses on the transfer of electron, the gaining and losing of electron for elements or for atoms participating in this kind of reactions. Okay, so throughout the unit, we are first going to define the oxidation, and we will see what oxidation actually means and how oxidation take place. Likewise, with reduction, we will look at examples for reduction and what reduction actually means compared to oxidation. And then we will look at the concept of oxidation reduction reactions, or what's also known as, excuse me, what's also known as redox reactions. Okay. Um, Once we finish the redox reaction, we will look and we'll try to learn how we can identify oxidation reduction reactions using the change in oxidation numbers for elements participating in this kind of reactions. And then at the end, we will look at different types of oxidation reduction reactions. Okay. So the type of redox reaction or the redox reduction oxidation reduction reactions actually happens all around us. When you're charging your phone, you're basically starting a redox reaction on your phone that results from gaining and losing electrons, and that's where the transfer of electron happens between the anode and the cathode, the positive part and the negative part. That transfer of the flow of electrons ended up generating energy, which at the end is stored on your device as an energy. Same thing if you're charging your car. So if you have an electrical car or a hybrid car, if you plug your car, that's exactly what you're doing. The battery that you have in your car is a cell that operates on the concept of a redox reaction. Even in a human body, a redox reaction is one of the main methodologies of generating energies in our body. So when you look in any human cell, the cell biology involves a redox type of reactions to generate energy in the mitochondria or in the powerhouse of the cell. Even forming cancer cells, it is also believed that it is as a result of a redox reaction on the human DNA, which happens due to the formation of the hydrogen peroxide throughout another other reactions in the human body. That's why the term, drinking a lot of antioxidants, trying to have a diet with a lot of antioxidants, because what you're doing basically, you're removing something like hydrogen peroxide, which is considered an oxidizing material. Okay, so the term redox reaction, it's fairly common when it comes to energy generated either in a human body or, like we said, about generating batteries, generating energy for batteries in general. Redox reaction is also something that we have seen. I'm pretty sure everybody have seen this, with their naked eye. That if you're looking into any layer of rust over iron, for example, that orange layer that you see, that's basically a rusted iron um, or iron oxide, some form of iron oxide, either the second or the third. So that is another type of oxidation reduction reactions. Okay, so oxidation reduction reactions, again, it's a chemical reaction where electrons are transferred from one atom to another atom. So if you're looking, for example, at this reaction of magnesium and oxygen, what we notice here, we notice a change in the oxidation number of the magnesium, because the magnesium starts with a full count of electron with oxidation number of 0. And when we say oxidation number of 0, that means the atom of the magnesium at this point, it's a neutral atom. It does not carry on any charge. Likewise with the oxygen has the complete count of electrons. It did not really gain or lose any electrons. So the count of electrons is 8, which means oxygen is also neutral, just like the magnesium. But once you combine both together, a redox reaction takes place, which means you have magnesium has lost electrons, which consequently change the oxidation number for the magnesium to positive 2. When you look at the oxygen has gained these 2 electrons. So the oxidation number changed to negative 2. So magnesium now is short with 2 electrons. That means we have 2 more protons compared to electrons, so that's why it's a positive 2. And the oxygen now gained these 2 electrons, so we have 2 more electrons than what we have as protons. That's why it is a negative charge. So what we're trying to say here that there is a transfer of electrons. The electrons has departed or left magnesium, and it was grabbed by the oxygen. And that's generally what happens when any atom or any element reacts with oxygen. Oxygen is one of the most electronegative negative elements in the periodic table. Well, that means that electrons tend to grab and gain electrons all the time from whatever atom it is reacting with or whatever element it is reacting with. So magnesium in this case, which is in group 2 in the periodic table, reacts with oxygen, which is very high electronegative. Okay, so it's high electronegativity. So the electron gains these 2 electrons, and that's how we have the transfer of electrons. Okay, so oxidation reduction reaction, as we will look at more in depth later, uh, it entails an oxidation process and a reduction process combined together. An oxidation process, it's not cannot happen independently from a reduction process. If element is getting oxidized, these electrons has to be gained by another element. So a reduction counterpart has to happen. Okay. So what we say when we're looking at the magnesium in this case, because magnesium lost the electrons, we describe magnesium at this point as being oxidized. Okay. On the other hand, because oxygen gained those electrons, we describe oxygen as the atom that's being reduced. So we have an oxidized material or an oxidized substance, which is the magnesium, and we have a reduced substance, which is the oxygen. Okay. So what is oxidation? So as I said, oxygen is very electronegative. So frequently and often it will steal electrons from other atoms, just like what happened with the magnesium. So you'll see oxygen will take electron from magnesium, from sodium, from potassium, lithium, so on and so forth. When an element combines with oxygen, it often loses the electron to oxygen. Therefore, it's said to be oxidized. Okay, so being associated with oxygen is just good enough to make that element loses that electron. So that element, it is said to be oxidized. Many reaction involve transfer of electron, just like how we talked about earlier. And then you have to remember that this transfer of electron from a metal, which is the magnesium, so magnesium is a metal, and oxygen is a non-metal. So that transfer of electron from a metal to a non-metal, it should be really familiar to us because we looked at this one when we talked about binary ionic compounds, correct? Because with a binary ionic compound, you have one element, which is the metal, and we have the non-metal, and the non-metal normally takes the electron from the metal. Okay, so the oxidation reduction, it's not something really brand new to us as far as concept. This is something that we looked at before in the binary ionic compound. It's just we did not call it as such. Okay. Oxidation and formation of binary ionic compounds, something like NaCl. Okay, so this is a binary ionic compound, correct? Because sodium is from group 1, chlorine is from the halogens in the periodic table, so a metal and a non-metal. That means I have an ionic compound. If you're looking at the sodium atoms and the sodium atoms will lose the electrons to the chlorine. Remember, chlorine is on the halogen group of the periodic table. Chlorine and the halogens in general have a high electronegativity, so they will take the electron from sodium from group 1 in the periodic table. Okay, so chlorine will gain these electrons, sodium will lose these electrons, chlorine gain these electrons. Okay, so we have sodium ions or cations, and we have also chloride ions or anions with a negative charge. So in this case, if I were to describe A material that's been oxidized, that would be the sodium. The material that has been reduced, that would be the chloride, or the chlorine, I should say. Okay, so the chlorine gained these two electrons. Likewise with the oxidation of zinc. So when zinc reacts with oxygen molecule, oxygen, because it's a high electronegative, it will drag and grab these electrons from the zinc, which would result with zinc positive 2 and oxygen negative 2. So these two electrons left zinc, um, and have now been added to oxygen. Okay, so zinc lost electrons. That means oxidized. Oxygen, on the other hand, gained electrons. That means reduced. So the oxidation definition was actually redefined. So what was initially thought that oxidation only happens when there is a reaction with oxygen, and that was actually, as you saw earlier, that was refuted when we looked at the NaCl example, where we have oxidation and oxidation that actually took place without the involvement of oxygen. So the oxidation, like I said, definition was redefined to make it more broad, to cover any change, any chemical change, where at least there is one element that loses an electron. Okay, so it no longer only limited to the reaction with oxygen, like what happened with the magnesium and the zinc. It actually covers any change, any chemical change where you have at least one electron is lost. Okay, so if we kind of take a deeper look into the NaCl and break it down into the electron configuration of the Na and for the Cl, we notice that the sodium with its 11 electron has only one electron on the outer shell. The chlorine with its 17 electron has 7 electrons on the outer shell, and it's only missing one electron to complete the octet, right? And the octet, that's something we talked about in a couple lectures ago. So what happens, the sodium will lose that electron to the chlorine, so sodium is said to be oxidized and lost the electrons. Electrons now is gained by the chlorine. So oxidation is when there is an event of losing electrons, when there is a chemical change that involves losing electron or losing at least one electron, and that's what we call it oxidation. Okay, now in terms of reduction was also initially thought that it only take place when there's oxygen is involved. So an element is said to be reduced when there is a reduction in the number of oxygen bonding. Okay, so if you look at something like the zinc oxide, or the reduction of the zinc oxide equation, so zinc reacting with carbon under heat to form carbon dioxide and elemental zinc. And based on this definition, we can see that the zinc oxide no longer exists. So the zinc lost the bond with the oxygen, so the number of bonds of zinc with oxygen has been reduced. That's why zinc is considered a reduced element in this case, or reduced substance. Okay, so zinc is reducing the number of bonds to oxygen atoms. Historically, zinc was said to be reduced. But what actually is happening, zinc has gained two electrons from the carbon. Okay, so the oxidation state has changed from positive 2 to a 0, a neutral charge. Remember, every time you see a free element substance, the oxidation number for that substance is a 0. It is a neutral substance. Okay, so the zinc oxide, oxygen is a negative 2. Oxygen is always negative 2, and I will give you a chart for common oxidation numbers and how to calculate oxidation numbers. But there is anything that you would like to kind of memorize, it's probably for the oxygen. The oxygen is always a negative 2. Rare cases is a different oxidation number, but the one that we'll be covering is going to be a negative 2 only. Zinc in this case is a positive 2, right? So negative and can cancel the positive. That's why the zinc oxide total charge over the molecule is a neutral. It's a 0. So we notice that it went from a positive 2 to a 0 net charge, neutral charge, okay? Which means coming from a deficit of two electrons or two more protons, two electrons were gained to cancel out this two positive charge. So now the gaining of electrons is said to be reduction. So zinc has been reduced. Just like with the oxidation, the definition was restructured to basically go along with the oxidation definition. So the reduction is any chemical change at which one element gains an electron. Okay? And reduction, just like oxidation, they're both accompanied together. They never happen independently from each other. Gaining, losing electron, oxidation, reduction. I know this can be confusing a little bit. There is some acronyms that you guys, if you want to use to help you memorize, what is actually oxidation and what is reduction. So Leo says GER, for example, is one of the common acronyms that people use. So loss electron, oxidation, GER, gain electrons, reduction. Another common acronym that some people use is oil rig. So oxidation is loss of electrons, rig, reduction is gaining of electron. Oops, sorry about this. So gaining electrons, okay? Feel free to use either one of them. It helps you memorize which is oxidation and which is reduction, okay? As I have been saying since we started talking about Unit 7, oxidation and reduction always happens together, okay? Because electrons are not likely to be found separated from an element or compound. If you look in any chemical interactions where we have bond formation and bond dissociation, which involves transfer of electrons, you will never find electrons just kind of swimming around without being associated to a specific atom or specific element. As a result, oxidation and reduction reaction always happen at the same time. Reaction in which electrons are transferred, resulting in oxidation and reduction, it's called oxidation reduction reaction. Now, to make things a little bit easy, we refer to it as reduction reactions. So sometimes we would look at the half reaction equations for the redox reaction equation. So this equation that we're looking at right here for the magnesium oxide, magnesium and oxygen reacting together to form magnesium oxide. This is the redox equation. Okay, so this is the complete redox equation. If we were to break this down into two halves, the first half would be the oxidation half reaction, and the second will be the reduction half reaction. With these two half reactions, we can actually see where the electrons are coming from and where the electrons are going to. That's number one. Number two, we can also see the number of electrons that's involved in this oxidation reduction reaction. Okay, so we have 4 electrons coming from the magnesium and 4 electrons are getting gained by the oxygen. If I were to add and take the summation of these two equations, this will be 2 magnesium plus an oxygen. 4 electrons going to cancel with 4 electrons. So 4 electrons on the products of magnesium. I will cancel out with the 4 electrons that are gained on the reactants with the oxygen. So we can cancel these electrons. So this will give 2 magnesium ion plus 2 oxygen ion. But just because we have anion and cation, we don't really write it this way. What we do is we write them in their molecular configuration, which is 2 magnesium oxide. Okay, so this is the complete redox equation for this. The most important thing that we notice when we write the redox equation, that we don't see the electrons, not on the reactants nor on the products. That's something you have to keep in mind. When you're doing your total redox equation, from your two half reactions, you need to make sure that you're canceling out your electrons. The electrons you're losing on the oxidation reaction has to equal the number of electrons you're gaining on the redox reaction, so you can cancel both. If you're not getting the same number of electrons, you're doing something wrong. But regardless, electrons should not show on the complete redox equation. So let's break it down a little bit and look at the electron configuration of magnesium as well as oxygen and see how the electrons are getting transferred. So first, if you look at the magnesium, it has 12 electrons total with 2 electrons on the outer shell. Okay, so these 2 electrons are easier to lose than gaining 6 electrons to reach the octet. I think this is just common sense. So the 2 electrons, magnesium will always lose these 2 electrons. So that's why magnesium is known to have a positive 2 oxidation number all the time. And same thing with all the elements on a group 2 in the periodic table. Okay? Now oxygen has 8 electrons, so it only needs 2 more electrons to reach that octet rule. Now this is already being achieved in the oxygen molecule by sharing these 2 electrons in the middle. Okay? But when we are looking at the oxidation of the magnesium, for example, we see that 2 electrons on the outer shell, excuse me, they are no longer there. We lost these 2 electrons, okay? That's why we see 2, 4, 6, 8, and a 10, okay? Same thing happened with the second magnesium molecule. I'm sorry, magnesium atom. So it lost these 2 electrons. So in total, we have 4 electrons lost and 4 electrons gained by the oxygen. And you can see these 2 electrons standing out with 2 different colors. Okay? If we break down this redox reaction, what we see here, we actually see the 2 electrons in the redox. In the oxidation half reaction, these electrons are getting released from the magnesium atom. Okay, so the oxidation half reaction will always show the lost electrons in the product. So that's again, I'm trying to really highlight this because I will ask you to write the half reaction for the reduction as well as the oxidation. So when you're writing the oxidation, you need to make sure that the electrons on the product side, because we're losing these electrons. Okay? On the other hand, if you're looking at the reduction half reaction, the electrons would be on the reactant side. Yes, you guessed that right, because we're gaining these 2 electrons. So when we gain these electrons, they have to be on the reactant side, so the oxygen would accept these 2 electrons. So the oxygen is being reduced. Okay? So that's in terms of oxidation and reduction. The 2 new terminologies that I would like you to get introduced to is the reducing agent and the oxidizing agent. Okay, and things might get a little bit confusing here, but you just have to pay a little bit more attention, and we shouldn't have any problems. So with a reducing agent is the substance that loses electrons, which makes it possible for other substance to gain those electrons and be reduced. So a reducing agent is the substance that causes the other substance to be reduced. In other words, this is the oxidized substance. Okay? So the oxidized substance, it's always a reducing agent. So the reducing agent is basically a synonym to the oxidized substance. Okay? Because every oxidized substance is a reducing agent. We talked about this, intensively in the beginning of this unit, that when the substance is oxidized, that means another substance is getting reduced, okay? Because we can't just lose electrons. So that oxidized substance, it's also known as a reducing agent. Likewise with the reduced substance, because the reduced substance has resulted in oxidizing another substance. So we recognize that as the oxidizing agent. Okay? So these 2 new terms or terminologies, I'd like you to also keep them in mind: the reducing agent and the oxidizing agent. So the reduced substance is always the oxidizing agent. Um, how do we identify oxidizing and reducing agent? Magnesium atom, for example, has lost the electrons, so it has been oxidized, right? Lost the electrons, which allowed oxygen to gain those electrons. So in this case, magnesium is also considered a reducing agent. Oxygen, on the other hand, gained these two electrons. Oxygen reduced, right? Which allowed, I'm sorry, not zinc, but magnesium, to lose these electrons. So that's why oxygen is considered as an oxidizing agent. And this is the same equation that we talked about. So what kind of questions should I expect in the exam? That's probably the first question that pops in your head right at this moment. I will give you an equation and I will expect you to identify the oxidized material, or the oxidized substance, the reduced substance, the oxidizing agent, the reducing agent. So that's what you need to pay attention to. Okay? When it comes to oxidation and reduction in molecular compounds, it's a little bit different because when we say molecular compounds, remember we're talking about covalent bonds. Okay? With covalent bonds, what's happening is the electrons, the concept of covalent bond, the electrons are shared, are not gained nor lost, but shared. Okay? So the fundamental difference between these two reactions, between the nitrogen and oxygen and the magnesium and oxygen, this one is molecular compound or covalent bond, right? Because nitrogen as well as oxygen both are nonmetals, so it's going to form a covalent bond. While magnesium and oxygen, because it's a metal magnesium and a nonmetal oxygen, this is an ionic bond or compound. Okay? So the bond between the nitrogen and oxygen are covalent bonds. With electrons are, sorry, electrons shared and not transferred. So that's the main difference, or it's actually the fundamental difference between the nitrogen oxide and the magnesium oxide, that the bond is a covalent bond and the electrons are shared and not transferred. So what we call it in the beginning, or what we have been calling it as gaining and losing of electrons, in this case of nitrogen and oxygen, it's a partial loss and a partial gain of electrons. Just like when we talked, if you remember, about something like water, right? With hydrogen and oxygen, a covalent compound, and we said there was a partial positive charge for the hydrogen and a partial negative charge for the oxygen. Same thing for the nitrogen oxide. For the nitrogen oxide, there is a partial gain and a partial loss of electrons. So the electrons, not all the electrons are going to the oxygen, and not all the electrons are getting, or not all the electrons the nitrogen is losing. So the nitrogen oxygen bond is a polar covalent bond, right? This term should be familiar to you at this point. A polar covalent bond is when you is when you have two atoms bonded together with one atom has the ability to drag more electron than the other. Okay? In which oxygen atom attracts more electrons than the nitrogen atom. So there is a partial negative charge over the oxygen. There's a partial negative charge. Okay? It should be like this. You don't have to worry about the double bond. I'm just trying to show you the negative charge and the partial positive charge. Okay? The oxygen atoms gain electrons partially and still considered as a reduced substance. The nitrogen, on the other hand, loses the electrons partially and is considered an oxidized substance. Okay. So chemists have extended the definition of redox reaction to include partial transfer of electrons. And when we say partial transfer of electron, this happens only for molecular compounds or when covalent compound or when covalent bonds happens. Okay, so that is a partial transfer of electrons. Um, so overall, when we talk about redox, the reducing agent loses electrons and thus is oxidized in the reaction, and you have the oxidized the oxidizing agent gains these electrons. Okay, so when we say the reducing agent loses electron, that means oxidized. When we say the oxidizing agent gains, so the key word here is gain, that means reduced. We have, it accepts two possibilities. Number one, either a complete transfer of electrons, and in this case we have ionic compounds, or we have a partial transfer of electron. In this case, we have polar covalent bond. So this basically summarizes everything that we have been talking about. Okay, so let's review everything that we've been discussing about redox reaction. First, oxidation reduction reactions. It is electron transfer reactions. Just like with the precipitation reactions, those are reactions that form precipitate. Um, as part of the products. In oxidation reduction reactions, it's electron transfer reaction. Oxidation is the complete or partial loss of electrons. Remember, nitrogen oxide, we still considered the nitrogen the nitrogen as the oxidized material or the oxidized substance. Reduction is either complete or partial gain of electrons. Oxidizing agent is the substance that's reduced, so it gains the electron. So the keyword here again is gain. Reducing agent is the it's the oxidized material right here. So the oxidizing agent is the substance that is reduced, gains the electrons, make it possible for something to lose these electrons. The reducing agent, on the other hand, is the substance that's oxidized, so it loses the electrons, allowing other substance to gain these electrons. Okay, so probably I would consider this page very important to pay attention to. Okay. So now let's look into identifying oxidation reduction reaction using oxidation numbers, which I think that's the part that I find kind of interesting. So how can we tell what is the oxidation number? How can we tell this material oxidation status has changed from being positive to being negative, or changed from 0 to being negative? Um, so it's not really always clear if a reaction always involves a transfer of electrons. So there is a numerical system that we actually follow to keep track of electrons and allow reactions to be identified as redox reaction, because again, the only way to tell if it is a redox reaction by tracking the oxidation numbers of the substances involved in the reaction. If there is a change in the oxidation number, either gaining or losing, that means it's a redox reaction. The system also shows us which element is oxidized, which is reduced, and therefore we can identify the oxidizing and reducing agents. Okay? Well, first, here's some handout for you to help you out identify oxidation numbers, because this is basically touch the center of our subject here, how to identify oxidation numbers. Because once you're able to calculate the oxidation number for all the elements in the equation, you're basically halfway there to identify your reducing agent, oxidizing agent, so on and so forth. Okay, so here's the rules. Rule number 1. Pure elements, excuse me, pure elements always have an oxidation number of 0. Excuse me. So the oxidation number for each atom, something like zinc, will be considered 0. A diatomic molecule like hydrogen, oxygen, so H2. If you see H2 in an equation, or oxygen, or you see N2 in an equation, or you see S8, oops. What else? Let's see. F2, Cl2. All those guys will have a zero oxidation number. Those are considered pure substances. So they won't have a positive nor a negative oxidation state. They're not gaining or losing electrons. It's always a zero. H2O, for example, that's a different case. You can't consider hydrogen in this case as a zero, and you can't consider oxygen as a zero. We will look at this in a second. But the point here, pure substances always have an oxidation number of a zero because they are neutral. Okay, there is no electron transfer, gaining or losing. Monoatomic ions, you'll have to calculate the charge on the ion. Okay, so something like, let's see. So something like cadmium, for example, and cadmium chloride will have a positive 2. How would I know that? Because a chlorine on a group 7 in the periodic table will have a negative 1 oxidation number. So 2 of the negative needs a 2 of the positive. So that's how you calculate. We will do plenty of examples in a second. Same thing for the hydrogen and lithium hydride down here. So how would I know what is the oxidation number for the hydrogen, the single hydrogen, for example? Lithium oxidation number is a positive 1. Since the total charge over the lithium hydride is a 0, then the oxidation number for the hydrogen has to be a negative 1. So fluorine in the periodic table, which has in the same group chlorine as well, and iodine, so on and so forth. So those guys will always have a negative 1 oxidation number. Oxygen always have a negative 2. There are exceptions where oxygen will be a negative 1, but you don't have to worry about this. You can always consider oxygen as a negative 2 in our course. Hydrogen always has a positive 1 oxidation number all the time. Rare cases, which is a negative 1, but again, you will not see this one. So you only have to worry about a positive 1 oxidation number for the hydrogen. So what about other elements? So if a compound's formula contains one element, for example, that is not really covered by the table that we just looked at, what you need to do simply, you need to calculate that based on the known oxidation number of all the other elements involved in that molecular formula. Okay, so the sum of oxidation numbers of the atoms in the compound is equal to the charge of the compound. Well, what does that mean? So something like A subscript A, B subscript B. Okay, so you will have to the way to calculate the oxidation number, for example, for A, or even before that. So when you calculate the oxidation number for the total compound, that would be A. So that's a number multiplied by the oxidation number for the atom A plus B, which is the subscript number B accompanied to the atom B, multiplied by the oxidation number of B would be equal to 0. Now, why is it equal to 0? Because the total charge over the AB molecule is a 0. That is very important to pay attention to. Because when we look at the next example here, the CD, it has a negative 2 charge. So when we do the total charge, when trying to calculate the total oxidation number of all the compound or all the atoms involved in this molecule, will have to equal to negative 2 because the charge over this molecule is a negative 2. And that's how you calculate the oxidation number for something unknown inside a chemical inside a molecular molecular formula. Okay. Rules that you have to pay attention to, and again, I'm saying that multiple times. Please ignore coefficients when you're calculating oxidation numbers. Coefficients are really not important in this case, so you don't have to worry about factoring in the coefficients when you're calculating the oxidation number. Now remember, when we say coefficients, those are the numbers that we add when we balance the equation. These should not be included when you're calculating the oxidation numbers. And again, we're not talking about the subscripts. We're talking about the coefficients, the big numbers that we add ahead, for example, like a 2 or a 3, to make sure our equation is stoichiometrically balanced. Okay, so the coefficients are not involved in the calculation. Okay, let's try some practice problems and try to calculate the oxidation number for element for elements using the table that I just showed earlier. Okay, so first one we have here is the RBH, which is the rubidium hydride. Obviously, from looking at that table, we know that hydrogen always has an oxidation number of a positive one, and the total charge for the rubidium hydride is 0, right? You don't see any charge above this molecular compound. Okay, so what that means that the total oxidation number of the rubidium plus the hydrogen will be equal to 0. So I'm going to refer to the oxidation number for rubidium as an X plus positive 1 would be equal to 0. Okay? So at this point is pretty much straightforward algebra. So what I will do, I'm going to add a negative 1 on both sides. So I can cancel out my positive 1. Okay? So X would be equal to negative 1. So the rubidium RB oxidation number in this case is negative 1. Okay? Let's look at the ammonium. Once again, hydrogen, based on the table that I just showed you, always is a positive 1 oxidation number. And now we're trying to calculate the oxidation number for the nitrogen. The total charge for this molecule is a 0. There's no this molecule does not carry on any charge. So the net charge here equal to 0 for all oxidation numbers. So for the nitrogen, I'm going to refer that one as an X plus I have 3 of the hydrogen based on the subscript. So I have 3 times positive 1, and that would be equal to 0. So X plus positive 3, right? Because 3 times positive 1, and that would be equal to 0. In order to get rid of my 3 on the left side of the equal sign, what I will do is I'm going to add a negative 3 or subtract 3 on both sides. So cancel out, and then X or the oxidation number for nitrogen will be equal to negative 3. Let's try nitrogen molecule or molecular nitrogen. So in this case, because nitrogen is a pure substance, it will have an oxidation number of a 0. So every time you see a pure substance like a nitrogen, same thing for the H2, for the O2, for the O2, for the F2, for the Cl2, etc. You get the idea. The oxidation number for such compounds will be a 0. Okay. Let's look at the last one that we have on the slide, which is scandium oxide. Okay. So oxygen always has a negative 2 oxidation number. Okay. It doesn't matter what is the other element that it's associated with or it's bonded to, the oxidation number is always a negative 2. So when I'm trying to calculate, I'm trying to figure out what is the oxidation number for the scandium. Okay. Okay, so I'm going to refer to that one as an X, but since I have 2 of the scandium, then that will be multiplied by 2. Plus, for the oxygen, it's a negative 2, but I have a 3 of the oxygen, right? So I have 2 of the scandium and 3 of the oxygen. The total net charge for this molecule is a 0. So it's going to be 2x negative or minus 6, right? 3 times negative 2 equal a 0. So what I'm going to do, I'm going to add a positive 6. I'm going to add a 6 on both sides of this equation. So the 6 is going to cancel out with a 6. And 2x will be equal to 6. And now what I will do is I'm going to divide both sides by 2. So x will be equal to 3. So scandium oxidation number is a positive 3. So why doing this kind of practice? Because later when we will be doing examples or questions in the exam for oxidation reduction equations without really calculating the oxidation numbers of your reactants, as well as products, you're not going to be able to identify oxidation, oxidizing agent, reducing agent, oxidized substance, and reduced substance. Okay, so it's very important for you to be really comfortable doing these calculations, so you can figure out the oxidation number for these elements, and as a result, you will be able to identify all the elements of the redox equation. Okay, redox equation. Let's do more practice. So on this one here, for the nitrogen, for the dinitrogen tetraoxide, we're trying to calculate the oxidation number for the nitrogen. Now, why not calculate the oxidation number for the oxygen? Because oxygen, as I said earlier, always has a -2, and you can memorize that off heart, has a -2 oxidation number. So nitrogen is the one that I'm trying to figure out the oxidation number for. So in this case, just like how what I have been doing before, this will be an x, but since I have 2 of the nitrogen, so this will be multiplied by 2. Always pay attention to the subscript. Plus, for the oxygen, it's a -2, but because I have 4 of the oxygen, so this will multiply by 4. Equal to, and instead of having it equal to 0 like the previous examples, we see here this compound has actually a total charge of a -2. So the summation of all oxidation numbers will be equal to -2 for this specific compound. Okay, so now it's a simple math. Let's try to figure out what the value for x is. So 2x, 4 times 2, so that would be -8 equal -2. Now what I will do is I'll be adding a +8 on both sides. So 8 is going to cancel out with this 8. And this will be +8. So 2x will be equal to +6. And then I'll divide by 2 and equal to 3. So the oxidation number for nitrogen in this case is a +3. +3. Now let's try to calculate the oxidation number for nickel sulfate, NiSO4. For the nickel sulfate, we know the oxidation number for nickel is +2. How do we know this? Because we know the SO4 has a net charge of the polyatomic ion sulfate has a 2 negative charge. So in order for this total compound to have a net charge of a 0, 2 will have to cancel out the 2. Or, in other words, if you remember, and we do the swapping, so that means Ni2SO4 2. It's just because both are 2, we cancel out the 2's. So the oxidation number for the nickel is a +2. For the oxygen, it's a -2, and that we should know at this point. Okay, so what we are trying to calculate, we're trying to figure out the oxidation number for the sulfur. All right, let's do that together. So for the nickel, that would be a +2. For the sulfur, that's our unknown, plus 4 times -2, all equals to 0. Now I'm trying to solve for x. This will be a -8. So positive plus 2 plus x minus 8 equals 0. So I'm going to do this operation here. 2 minus 8, that would be x minus 6 equal 0. And then the oxidation number for the sulfur will be +6. Let's do another one. Let's do the hydrogen phosphate. So for the phosphate, we know that the phosphate has an oxidation number of -3, right? So PO4, the phosphate polyatomic ion, always has an oxidation number of -3. So when you're trying to calculate, in this example, when you're trying to calculate the oxidation number for the phosphorus, right? Because the hydrogen, we know it's a +1. For the oxygen, we know it's always a -2. So our unknown in this case is the phosphorus. You can do this two different ways. You can either figure out the oxidation number for the phosphorus from the phosphate and just work on the polyatomic ion molecular formula, or you can do it with the hydrogen. Both ways will give you the same results or the same oxidation number for the phosphorus. Let's do it with the hydrogen, and then I think we will have another example later. Um, we'll do it for the phosphate only. Okay, so for the hydrogen phosphate, for the hydrogen is a +1. For the phosphate, that's our unknown. Plus, for the oxygen, it's 4 times -2. And that would be equal to -2. Because the total charge we have here is a -2. Okay, so the summation of all oxidation numbers will be equal to -2. So now I have 4, that would be a -8 with +1 here, so x minus 7 equal -2. So what I will do is I'm going to be adding 2 on both sides. So I can cancel, oh, I'm sorry, I will be adding 7 on both sides. So I'll be canceling out my 7 with the x. So 7 is going to cancel out with the 7. And this one will be +7. So x will be equal +5. +7. And this is negative. So x will be +5. And that's the oxidation number for the phosphorus. Okay? So let's do the last one that we have here, the manganese phosphate. And I'm running out of room, so what I will be doing, I'll be doing the manganese phosphate up here. So that is the manganese phosphate. What is the oxidation number for the manganese? The oxidation number for the manganese is represented by the subscript that is multiplying by the phosphate, because the manganese and the phosphate, PO4, -3, they were swapped using this technique to figure out the molecular structure or the molecular formula. Okay, so the 2 that we see here, this is from the oxidation number for the manganese. And the 3 we see here, this is from the total charge of the phosphate polyatomic ion. Okay, so the oxidation number for the manganese is 2 positive. For the phosphorus, that's the one that we're trying to calculate. Okay, for the oxygen, it's a -2. So in order for you to calculate the oxidation number for the phosphorus, there is a long way and there is a short, easy way. I think the long way is not only time consuming, but it's also prone to making mistakes. So let's do the long one first, and then I will do the easy one later, which I hope that everybody will be doing. So to calculate the oxidation number for the phosphorus, first, manganese, so it's 2 times 3, because I have 3 of the manganese, right? Plus, I have 2, and I'm going to open my parentheses, because this 2 here applies to the oxygen, and it applies for the phosphorus. So I need to be really careful, and that's where mistakes could happen. So it's going to be 2 parentheses, x, that's the oxidation number for the phosphorus that I'm trying to calculate, plus 4 times -2. Okay? So let's try to solve for x here now. So 2 times 3, that would be a 6, equal to 4, that would be 8. So, So that would be 6 plus 2x minus 16 equal to 0. Once you finish doing all the calculations, phosphorus oxidation number will be equal to +5. So this is the long way of doing it. The short way of doing this that you can basically just work on the polyatomic ion, which is the phosphate right here. Okay? So what I'm going to do here, I'm going to just do following the total oxidation number for the phosphate. I'm going to calculate the oxidation number for the phosphor. So phosphorus will be X plus 4 times -2. That would be -3. So X minus 8, right, equal -3. I'm going to add a positive 8 on both sides so I can cancel out my 8. As a result, P oxidation number will be positive 5. And it is obviously the same thing as we calculated up there. Okay? So you can either calculate for the phosphorus using the entire molecular formula. You just have to be careful with the parentheses, applying the subscripts, and make sure that you're doing your math correctly. Or you can just work on the polyatomic ion in this case, which I think that would be a lot easier. Okay, so let's refresh one last time before doing examples for redox equations. So first, if the oxidation number of an element changes through the course of a reaction, that means it's a redox reaction. So if you look at a chemical equation and you calculate the oxidation numbers, as we will do in a second, for all these elements, and then you find out that some of the oxidation numbers is actually changing between the reactants and the products, then that's a sign it's a redox reaction. If there is no change in oxidation numbers, then it's not a redox reaction. When the oxidation number of an element increases, it means that specific element has lost the electrons, so it's being oxidized. And I think that's where the most confusing part, comes from. So when you're doing the oxidation numbers, when the oxidation number is increasing, again, when we say increasing, that means we're having more protons than electrons. That means we lost the electrons, so the element has been oxidized. On the other hand, if the oxidation number of an element decreasing, so if it decreases, that means you're gaining, you're accepting electrons, so that means it's reduced. The reactant containing the element that it's oxidized, we call that reactant as the reducing agent, right? Because that compound allowed other substance to be reduced, so it is the reducing agent. On the other hand, the reactant containing the element that is being reduced, we describe that as the oxidizing agent. These are the things that you should expect to be asked during the exam. So I would give you an equation just like the one that you're looking at now, the color-coded one, and I will ask if this is a redox reaction or not. So now let's put everything together as far as oxidation agent, reducing agent, calculating also the oxidation numbers, just like how we did with the few practice problems that we did earlier. Let's put everything together and see how or what is the expectations during the exam. So something like this, you should most likely expect yourself to see it in the exam as well as during the homework, which you would be given an equation, and then you'll be asked if it is a redox equation or not. Now, obviously, you're not going to just guess that, but what you will need to do is you'll need to assign oxidation numbers to all the reactants as well as the products. When you identify change in oxidation numbers, either increase or decrease, that's when you can basically see where is your reduced and oxidized substances. Okay, so first what we need to do is we need to determine the oxidation numbers for all atoms. This might sound a little bit too much maybe at first, but then if you follow the table that I just gave you earlier, it's a very easy process. Okay, and then like I said, you will compare the oxidation numbers on both sides of the arrow to see where is your reducing agent, oxidizing agent, and so on and so forth. So all the practice problems and all the practice that we have been doing and on counting and figuring out oxidation numbers comes in handy when you're trying to when you're looking at a redox equation. Okay, so in this case, for the calcium phosphate, for the silicon oxide, for the carbon, for the phosphorus, for the carbon monoxide, calcium silicon oxide, what we will be doing is assigning oxidation numbers for all these atoms. That means for calcium, for phosphorus, for oxygen, so on and so forth. So following that table that I gave you, first thing first, what you need to do when you're trying to assign oxidation numbers, look for pure substances because those will always have a zero oxidation number all the time. They're neutral atoms or neutral molecules that carries no oxidation number. Do I have any pure substances in my equation at this moment? Yes, we do. We have the carbon, which will have a zero, and we have the phosphorus, which will also have a zero. So here's two out of the way, okay? Next, I would try to locate all the oxygens because we know the oxygen will always have a -2 oxidation number unless it is a pure substance, then at that point we'll have a zero. Do I have any oxygens? Yes, of course. I have an oxygen in this case with with the calcium phosphate, with the silicon oxide, a -2. I have a -2 with a carbon monoxide, and I have a -2 with a calcium silicon oxide. Okay. So, do I have any other hydrogens? Do I have anything else that I can use the table for? Yes, I have. I have the calcium, which we know it is in a group 2 in the periodic table. So calcium will always have a +2 oxidation number, and it will have a +2 oxidation number on the other side. Okay, so now I am left off with the phosphorus. I am left off with the silicon in this case, and I'm left off with the carbon and the silicon with the product. So from starting with about six, maybe or seven atoms trying to calculate the oxidation numbers, we're down to about three or four. Okay, just knowing how to use that table. So first, let's calculate for the phosphorus. So for the reactants, what I have the phosphorus and I have the silicon. That's essentially what I'm missing for the oxidation number. So what I'm going to do is I'm going to calculate for the phosphorus first. So for the phosphorus, just like how we did with the hydrogen phosphate, with the manganese phosphate earlier, you can either do the entire molecule, which is a very long way of doing it, or you can just do the polyatomic ion. In this case, I'm going to just target the polyatomic ion. So for the PO4, we know it is a -3 all the time. It's a polyatomic ion. Okay, and I'm trying to calculate the oxidation number for the phosphorus. So in this case, this will be X, referring to the oxidation number for the phosphorus, plus 4 times -2 equal to -3. Never forget the subscript down here. People tend to forget the subscript, which would result in incorrect oxidation number. And then you can't really, basically everything goes off from there because you're not going to be able to correctly identify the oxidizing, reducing material, reducing and oxidizing agents, so on and so forth. So paying attention to your subscripts, to the math when you're trying to solve for the oxidation number, it's very fundamental to this kind of problems. Okay. So let's try to solve for x. So x will be -8 equal to -3. What I will do is I'll be adding 8 on both sides, so I can get rid of the 8 with the x, and x will be +5. So the oxidation number for the phosphorus is +5. And I'm going to box this one. Now let's do the silicon. So phosphorus is a +5 in this case. And from here, you can probably see there's already a change in oxidation number for the phosphorus. I'm not going to call it anything at this point, but I just would like you to pay attention. So the oxidation number has changed from from +5 to 0. So the oxidation number has dropped, okay? Let's look at the silicon. So for the silicon, I have SiO2. So the oxidation number for the silicon, that would be an X plus 2 times -2 equal to 0. X equal positive 4. So the oxidation number for the silicon is a positive 4. So this one will be a positive 4. Okay? Let's now do our products. So for the products, we have carbon and we have the silicon. So these are the two that I need to complete my oxidation number set, basically, to try to figure out if there is any change in oxidation numbers. So for the carbon I have CO, which means we'll have X plus negative 2 equal to 0. X equal to positive 2. So the oxidation number for carbon is positive 2. This one is a positive 2 for the carbon. For the calcium silicon oxide, all right, so it's CaSiO3. For the calcium, it's a positive 2. For the silicon, it's X plus 3 times negative 2. If you do the math for this one, the silicon oxidation number will be positive 4. So silicon will be positive 4. The oxidation number didn't really change. Okay, so what do we have here? We have the phosphorus oxidation number changed from being a positive 5 to a 0. So phosphorus oxidation number has dropped, right, from positive 5 to 0. That means it gained electrons. So phosphorus will be reduced, or the reduced material, the reduced substance, okay? So what we say in this case, calcium phosphate is the reduced substance. Okay? As a result, it is also the oxidizing agent, right? Because it allowed another substance to be oxidized. Now let's try to find out what is that substance. The silicon and the oxidant didn't change. The carbon did change. The oxidation number has increased from 0 to positive 2. Okay, so we can say that carbon increased in oxidation number, as a result oxidized. Okay, oxidized, that means it is the reducing agent. So what we did, basically, we assigned oxidation numbers for all the atoms, for all the elements, and then we traced these oxidation numbers to try to identify any change in oxidation number, and then we were able to pinpoint our reducing agent, our oxidizing agent, reduced substance, and oxidized substance. This kind of question you should expect during the exam, and that's exactly what I will be asking for, to identify your elements of the redox equation. Okay, let's try one more example. We're going to try to identify our oxidized substance, reduced substance, reducing agent, and oxidizing agent. But before we do any of this, we will need to assign oxidation numbers. Following the table and following what we did in the first example, first, we need to find out if we have any pure substance, because these are the easiest to assign oxidation numbers since they will have zeros. Do I have any pure substances in my reactants? Yes, I do, which is the oxygen. Oxygen will have a 0. Same thing in my product, which is the chlorine, will have a 0 oxidation number. So here goes the chlorine and the oxygen out of the way. Next, I need to find out to have any ionic compounds, then I can assign these oxidation numbers as well. Yes, I have potassium chloride. Potassium is in group 1 in periodic table, so it'll have a positive 1 oxidation number. For the chlorine, we'll have a negative 1 oxidation number because it's part of the halogen group. Hydrogen always has a positive 1 based on that table. Nitrogen, we're not really sure. Oxygen is a negative 2. Oxygen always is a negative 2, which makes it also a negative 2 with a potassium nitrate, and makes it also a negative 2 in the water. Potassium here, it's a positive 1, always a positive 1. Nitrogen is unknown, so nitrogen here remains our unknown. Chlorine is a 0, it's being assigned, and hydrogen is a positive 1 all the time. Okay. So what do we have here? We have nitrogen is the only one that it's missing in the products. And nitrogen is also the only one missing in the reactant. So how about we calculate the HNO3 oxidation number for the nitrogen? Now, we can either do the HNO3 as a whole, or we can just do the nitrate, the NO3, the polyatomic ion. And that's what I'm talking about. But in this case, I'm going to do just the whole thing because we did the phosphate earlier, just the phosphate, the polyatomic ion. But in this case, I'm going to do the whole molecule so you can see how both ways are done. So for the hydrogen, it's a positive 1. For the nitrogen, our X is our unknown. And for the oxygen, it's 3 times negative 2. Now, if you do the math for this one, the nitrogen will have a positive 5 oxidation number. So the oxidation number for the phosphorus, in this case, for the nitrogen, is going to be a positive 5. I'm going to let you do the math for the KNO3. And this one will also have a positive 5 oxidation number. So at this point, every element or every atom has been assigned an oxidation number. I just need to track if there is any change between the reactants and the product. Potassium never changes, okay? Chlorine is a negative 1, and then it's now a 0. So the oxidation number has increased from a negative 1 to a 0. So chlorine, KCl, So chlorine from negative 1 to chlorine is a 0. So the oxidation number has increased, right? So we say that KCl is reduced. Okay? Okay, let's do another example. Again, we're going to try to identify our oxidized reduced substance, and then reducing agent and oxidizing agent, so on and so forth. But first, we need to assign oxidation numbers. First, I'm going to look for pure substances because those are the easy to start with, the easiest. For the oxygen is a 0, and for the chlorines also is going to be a 0 because they both are pure substances. Then, I look if there is any other oxygens because oxygen will always have a negative 2 unless if it's a pure substance. So I have an oxygen here would have a negative 2, and then I have an oxygen here with a potassium nitrate, they'll have a negative 2, and there is also a negative 2 in here. Do I have any hydrogens that I can assign oxidation numbers? Yes, I do. I have a positive 1, and I have a positive 1 here. So that takes care of my hydrogens. Now I have also an ionic potassium chloride. So potassium will always have a positive 1 because it's a group 1 in periodic table, and chlorine will always have a negative 1 because it's part of the halogen group. Okay? Now likewise here, this will always be a positive 1. So the only one that I have missing, basically, I have the nitrogen on both products and reactants. And then once I have the nitrogen, all the elements at that point will have oxidation numbers. Then we can identify our reducing and oxidizing an oxidized substance. So for the nitrogen, for the HNO3, I can either figure out the oxidation number for the nitrogen from the nitrate, or I can just do the HNO3 as a whole. So what I will do is, I'll do the HNO3 just to take it sort of a long way, so you can see, because when we did the phosphate, we did the calcium phosphate, we did just the phosphate. So in this case, if I want to calculate for the nitrogen, +1 for the hydrogen, plus x plus 3 times -2. X minus 6 equals 0. And then the oxidation number for the nitrogen is +5. Now for the KNO3, the oxidation number should also be +5, and I'll let you figure that out. So this will be +5, and this will be +5. So now, do I have any change in oxidation numbers? Potassium didn't really change. Chlorine, it is a 0, and it had increased to from -1 to 0. Okay, so we can see that from chlorine from -1 to chlorine a 0. That means the oxidation number has increased. That means chlorine has been oxidized. It lost electrons, right? From having one extra electron to being a neutral, right? So it lost that extra electron, so it's being oxidized. So we say KCl, oxidized substance. Okay, so here's my oxidized substance. So it is then the reducing agent. Let's try to find out if there is any oxidizing agent. There should be an oxidizing agent and reduced substance. Hydrogen oxidation number didn't change. Nitrogen did not change. Oxygen is a -2 here, and it's also a -2 here. However, if I look at the elemental oxygen, the oxidation number has dropped from being 0, from oxygen being 0 to H2O. Let me do this. Oops. H2O being at -2 for the oxygen. Okay? So the oxidation number has dropped. That means oxygen is the reduced substance. Okay? And likewise with the oxygen in the nitrate as well. The oxidation number also changes from 0 to -2. So either the nitrate, the potassium nitrate, or the water, both ones would be considered we would consider both changes as oxygen being reduced substance. So if you were to say oxygen 0 to potassium nitrate, that would also be considered correct. So oxygen in this case is the reduced substance, and it is the oxidizing agent. Okay? So that's how you find out where's the oxidized substance, where's the reduced substance, and that's how you can label um, um, all the reactants and the products correctly. Okay, so first thing first, you need to make sure that you're assigning the correct oxidation numbers, doing the calculations correctly, and then try to trace where is the change in oxidation numbers taking place, and that's how you can identify your substances. So to review everything together, oxidizing atom is the atom that lost electron. The change in oxidation number is increasing, so it increases in oxidation number. That means we're having more proton, less electrons, and that's how the number of oxidation number goes up. Okay, it's considered compound containing oxidized atom is considered a reducing agent. Okay, a reduced substance, on the other hand, that means when the element or the atom is accepting and gaining more electrons. That means you're having more electrons than proton, more negative charge than positive charge. That means the oxidation number is dropping down. So it is decreasing. And a reduced substance is also considered an oxidizing agent because it allows other substances and other atoms to be oxidized. Okay. When it comes to types of redox reactions, there is basically four types that I would like you to be familiar with, which is the combination reactions, decomposition, combustion, and single displacement reactions. Just like how we did the double displacement, now we're having the single displacement, and they are all considered redox reactions. In other words, if you were to calculate the oxidation numbers in this case, you'll find out there is oxidizing agent, there is reducing agent, that is change in oxidation numbers between the products, between the reactants, as well as the products. Okay? The combination reactions, it's when you have two or more elements or compounds combined together to form one compound. So, how can you tell if this is a combination reaction? Most of the times, you start two or three substances on the reactant side, and you will always end up with one product on the product side. That means you'll have that's how you have a combination reaction when you have multiple elements or molecules or compounds reacting together to form one substance in your product. So in this case, when you have sodium and chlorine reacting together to form sodium chloride, you have only one substance. You have a combination of two elements or two compounds. Okay, same thing with carbon and oxide. You have carbon dioxide, or magnesium oxide and water. You have magnesium hydroxide. So your the way that you can identify combination reactions by looking at your product and you're looking at your reactants. If you have two or more or multiple two or more reactants and you have one product, that's a combination. That's a combination reaction. Decomposition reaction, it's basically the opposite of combination reaction. When you have one compound, it's converting into two or more simpler substances. So you'll always start with one reactant and you will end up with two or more products. Okay? So for example, when you look at water, with a electric current as a catalyst, you will have two products. So you started with one, and you're ending up with one and one. You have two. You have two product. You have two products, which is the hydrogen and the oxygen. Okay. Likewise with the sodium chloride, with electric current as a catalyst, it will break off and dissociate and decompose and form sodium and chlorine gas. So you're starting with one compound, one molecule, and your products is two or more. So another example of a redox reaction is the combustion reaction. Combustion reaction is a redox type of reactions in which oxidation happens very rapid, and it's accompanied by heat and usually light, and sometimes also energy. So car engines, gasoline car engines, runs on combustion type of reaction, which is a redox reaction. As a matter of fact, this is not only the redox. This is not the only redox reaction that happens in the car, but the catalytic converter in the car that basically converts all the carbon monoxide into carbon dioxide using precious metals like the palladium, for example. It's also a redox type of reaction. That's why I don't know if you've followed the news, but there's always incidents of stealing catalytic converters because it has precious metals. Okay, they use these precious these this kind of metals to allow for a redox type of reaction take place to convert the carbon monoxide into carbon dioxide. So it's less environmentally harmful. Okay. So the combustion reaction is accompanied by light as well as heat. So you have propanol here, for example, reacting with oxygen to form carbon dioxide and water. The combustion reaction usually is expected to have oxygen as part of it. So that's a sign. So if you look at a chemical equation which has oxygen as part of it, it's a good chance that it's a combustion type of reaction. So oxygen is part of the reactants. It has to be part of the reactants. Otherwise, it will not be considered as a combustion reaction. When a substance that contains carbon is combusted or burned, carbon forms carbon dioxide. Okay, so gasoline in the car, for example, it's um, it's um, it's an organic compound that contains or mixture, organic mixture that contains a bunch of branched hydrocarbons of carbon and hydrogen. So when it burns, it forms carbon dioxide. When you have a substance that contains hydrogen, it forms hydrogen and in a form of water. Okay, so hydrogen comes out in a form of water. When a substance that contains sulfur, it comes as sulfur dioxide, like in this case. Okay, as you see here, when we're talking about combustion, all of these reactions has oxygen as part of it. Um, that's why it's considered as a combustion reaction. With a single displacement, just like how we looked at the double displacement reactions and precipitation reactions, um, and also in acid base reactions, this is a single displacement. So instead of having two elements displacing each other, there will be only one element being displaced in a specific compound. This is the general formula or the generic generic equation for the single displacement reaction. So in this case, if you look at the zinc reacting with copper sulfide, you will see that the zinc is basically, or the copper is being displaced by the zinc. So it's a single displacement reaction because it's happening with only one element that's being displaced and replaced by another element. Same thing with the cadmium here with the sulfuric acid. Chlorine and sodium iodide. You will see also the chlorine is taking the iodine spot basically, and it's being replaced. Um, uh, it's replacing basically the iodine and the sodium iodide. Okay, so in the exam, I might give you some equations, different types of redox reaction, and I would expect you to label which one is the single displacement, which one is the combustion, which one is the decomposition, which one is the combination reaction, so on and so forth. So these are the formulas for the redox type of redox reactions. With the combination reactions, as I said earlier, where you have multiple two or more reactants reacting together to always form one substance in your product. The decomposition reaction is the opposite of the combination reaction. So you'll have one reactant forming two or more products. Combustion, compounds that contains carbon, and it always has oxygen as part of it, containing carbon dioxide and water. The single displacement, similar to the double displacement that you guys should be familiar with, is just one element displacing another element instead of having the event happening twice in the chemical equation. Okay, so at this point, this takes care of Unit 7. As always, if you have any questions, always reach out.